The title of the talk is a bit general, that's I intended it to be that way, although we're going to be talking about a very specific thing. In particular, we've heard about the past few days, we've heard about all these amazing techniques. We've got QAPI, we've got tempo, ACE, polar and transform master equations, quantum algorithms. But there's a specific, very powerful technique that hasn't been discussed, okay? And interestingly, a very powerful method that you can use to study non-Markovian systems is by looking at Markovian systems, okay? And you can do that in a tractable way. If you want to study non-Markovian systems via Markovian systems, that comes at a cost, but it's a cost that you can keep under control, and you can do tractable calculations using our favorite ansatz, which is MPS, MPO, so on and so forth, okay? In general, I hope this blows your mind. You can do that in a thermodynamically consistent way, okay? So in your language, that would be your correlation functions in time are consistent with what you expect from thermodynamics from a Lindblad setting, okay? 2 remarks before I begin. The bulk of the talk is based on these papers. I'm going to be referring to other papers in other works, but the bulk of the talk is basically based on these papers. The rest of the results, I'll just mention them because they're a bit more advanced, and I don't want to muddy the waters here. I just want to bring you into this new, fresh perspective that hasn't been introduced in the past few days, okay? The second thing is that it's a very important day. Today is Costa Rica's Day of Independence. People go outside on the streets, they wear these very nice costumes, they party, they go out on the streets and dance. Mostly we drink. But I just wanted to share it with you. All right, before I get to the meat and potatoes, I want to discuss what's the meaning of a Markovian embedding, okay? Consider our usual scenario. We have a system coupled to a bath via some interaction Hamiltonian at the top, okay? This is the type of problems that we're interested in this conference, where we want to study the problem without making the assumption that we have a vanishing interaction between the system and the bath, and that no Markovian effects are at play, okay? A Markovian embedding is basically a mapping that allows you to bring certain degrees of freedom of the bath onto your system, okay? This mapping can always be made. It's an exact mapping, and there's always a way to do it macroscopically. The problem is that it's oftentimes not useful. It is only useful if after the mapping, this H tilde interaction term can be kept weak in the energy scales of the rest of the problem. If you can do that, then you can study this enlarged system in a Markovian embedding, okay? That's basically it. This bit here, H tilde B, is what we call the residual bath, okay?
Why would the rest be necessarily Markovian?
Okay, once again, I enlarged the system by including some degrees of freedom of the bath onto your system. That mapping you can always do, okay? But there are certain kinds of mapping for certain spectral functions that after the mapping, after you do the mapping, you end up with an interaction term that is weak compared to the rest of the energy scales in your problem. And in such a way, you can justify a Markovian approximation. That's it.
Just because it's weak counting?
Yeah.
Markovian?
Yeah.
I don't know why this.
It could have structure. Yeah. Let's take it by example. Maybe that's the better way. The most basic form of a Markovian embedding is a reaction coordinate mapping. Yeah, Kevin.
So that's sufficient, but not necessary, I would say.
For Markovianity.
Yeah, because there are these Rigotti Hamiltonians that can be strongly interacting, strongly coupling, but still give you.
Okay, let's put it very simple then. Let's put it in I'll make it very simple. for certain cases, for certain spectral functions, and for certain Markovian embeddings, you can employ the Markovian approximation and get the correct dynamics of the reduced state that you have here. Let's just make it like that. Okay. The most basic form of a Markovian embedding, most of you already know, is the reaction coordinate mapping. Okay. This is the most basic form. You have your system coupled to your bath, and then what you do is that you extract a single reaction coordinate that now becomes part of your system, and then your now enlarged system or your enlarged Hamiltonian becomes weakly coupled to a residual bath. Okay. There's a lot of things you can do with this type of configurations. Okay. There are only a certain class of spectral functions for which you can do this effectively, okay, in such a way that this enlarged system becomes weakly coupled to your residual bath. If you can do that, though, there's a lot of things that you can learn from the problem, okay? Let me show you one example. This is just a spin boson model with a single bath, the thermalization problem we've been talking about before, okay? These panels on the left is the coupling parameter, and the panels on the right is the temperature, okay? What I'm showing you here, the blue dots, let's take a look at the set component first of the spin. Before I start, I should mention that the system Hamiltonian is sigma z, and the coupling operator is this one that admixes sigma x and sigma z, okay? Just to be more general. The blue dots is the equilibrium value of sigma z as a function of the coupling strength at a given value of the temperature, okay? These diamonds here are results obtained from hierarchical equations of motion. This value here is the weak coupling limit approximation. This is the ultra strong coupling limit, which you can obtain if you're familiar with the works of Jan Anders, for instance. This can be analytically described for this model. And this here, this black line here, is a second order approximation to your thermal state, which is a further approximation that you can make on a thermal state, a strongish coupling, okay? That's the reason it works as strongish coupling, but not a strong coupling, okay? So it's very powerful. You can obtain both the sigma z component and the x component accurately. And at strong coupling, it also works very well for any given value of the temperature, okay? Very simple, very nice. And something which is very nice as well is that from this type of approach, nowadays there are certain transformations you can make onto the system, like Flatiron transformations and some truncations, in such a way that you obtain an analytical expression for an effective Hamiltonian that tells you what's the effect of strong coupling, okay? Very powerful indeed.
That the equilibrium state can be obtained with the Markovian approximation?
Yes.
The dynamics of
But the dynamics probably not. No, oh, sorry, no, the dynamics, yeah, not effectively. Sorry, because I'm talking about two different things here. If you have a reaction coordinate mapping like I have here, the dynamics are perfectly fine. The steady state and the dynamics as well. This was shown by Asang Nasir in Manchester. Yeah, maybe you want to take a look at those works. However, there's a way to obtain analytical insight from this by doing some Flatiron transformations and some truncations. If you do that, then you lose the dynamics, but you're able to understand the steady state very well. But the dynamics themselves, if you keep the mapping as I have it here, are perfectly fine for both the populations and the coherences, okay? I don't have the plots here, unfortunately, for the dynamics because I'm mostly interested in the equilibrium state, but I invite you to look at the works, for instance, of Asang Nasir or Philip Strasberg, who've done this in the past for the dynamics as well. And they have corroborated these numbers with the hierarchical equations of motion. Okay, not so fast. There's a huge caveat. There's only a certain class of spectral functions you can do this for, okay? Which spectral functions? There's a transformation after you do your reaction coordinate mapping. There's a way for you can understand the original spectral function and the newly mapped spectral function after you do the mapping, okay? You can only do this approach whenever you have a spectral function that after the mapping gets you something that's weakly coupled to your residual reservoir, okay? There's a list, basically, of spectral functions you can do this for. The one I showed you here is a Lorentzian one, okay? But there are other spectral functions you can do this for. For instance, if your spectral function of the original problem was ohmic, super ohmic, after you do the mapping, you'll get a spectral function that tells you that your system, your new large system, is not weakly coupled to your residual bath, and this will not work. Okay? In that case, having the spin boson model with the ohmic spectral function, super ohmic, so on and so forth, is a good benchmark for, in my opinion, at least new techniques, given that the most basic one doesn't work in that regime. Okay.
So if the spectral density has a lot of low frequencies, like a subohmic or an ohmic, you're saying that the dynamics will still be Markovian?
Again, if your spectral, you have an original spectral function, there's a mapping, and that mapping allows you to translate between a spectral function of the original model and the newly mapped model. I don't care about the frequencies of the newly spectral function. If I can make a Markovian approximation appropriately on that new spectral function, things will work.
Even if the new spectral function has low frequencies in it.
I don't really understand what you mean by that, so maybe we can discuss about it later. It's yeah. Okay, that's a huge caveat. Okay, but that's the most basic form of a Markovian embedding. What I'll be presenting to you now is another Markovian embedding, which is more general. This is just the most basic case. And that one makes no assumption about the spectral function. It can be any spectral function. Still, you can make a Markovian embedding, irrespective of that, at least for the fermionic case. Okay, let's start. Oh, yeah. I don't have to motivate my talk to this community, but I always like to, raise some examples via experiments, yeah? I brought two. This is one of my favorite experiments by Wolfgang Ketterle. These guys, in cold atoms, they're able to basically simulate integrable systems. The degree of control that they have over these platforms allows you to basically study the dynamics of integrable many-body quantum systems, and I think that's impressive, okay? This experiment is very nice because what they did was they studied the transport properties of the XXZ model, okay, using these very nice helicoidal initial states, and via some dynamics of the correlation functions, they managed to extract the transport exponents. And it's very nice because some of these exponents had already been predicted by theory and by numerics over the past 10 years or so. But it also showed some new behavior that people are now trying to investigate. And integrable systems are not like chaotic systems. Chaotic systems are a bit boring because they usually behave generically. But integrable systems have rich qualities at the level of transport and spectra. Okay. And the other one is this experiment that was shown to me by Ignacio Franco in Rochester. And these guys, what they do is that they have metallic leads coupled to these graphene layers. And even without the action of a voltage, of a bias between the leads, they manage to excite electron transport by shining light onto the graphene. So those are very interesting effects for which non-Markovian effects are at play, okay? And I'm gonna be using this example, actually, not the time-dependent one, but if you have like a many-body system here in the middle coupled to two leads, how can you solve that problem effectively, accurately, okay? So I like to use that type of scenario to motivate my talk. So we'll be looking at many-body systems coupled to two fermionic leads and see how we can solve them, okay? Let's get started, okay? So the type of configuration that we have is a system. We want to make no assumptions about the system, okay? It could contain non-quadratic interactions. It could be something very complicated, okay? And then we have thermal leads on both left and the right, and basic thermodynamics nets you what do you want to calculate at the level of the power, heat current, and the efficiency, okay? And the first question that you'll ask yourself is how do we address this, okay? How do we model the baths, okay? Let's start very nice and simple. One thing you can do is that for the sake of the argument, I'm going to consider a system with just a resonant level, okay? Just for the sake of this derivation, but at the end, this is going to be something completely general. We're going to have a reservoir modeled by a chain, okay? Some people may know this as chain mapping. Basically, you have a bath that couples locally to your system, okay? Via some interaction Hamiltonian. And as of right now, everything is quadratic, okay? So everything can be exactly solved. And in fact, we have a very nice theory to do this, which is the Landauer theory. And you can compute, even if this is a thermal state that you're putting here on your leads, you can compute currents, energy currents, particle currents, efficiencies, whatever you want. The thermodynamics of this problem can be all computed semi-analytically. I say semi-analytically because typically you require this transmission function. And depending on your system, this transmission function has to be computed via Green's functions. It's a very simple calculation, irrespective of what the system is, as long as it's quadratic, okay? But let me take a look at this lead, okay? I'm just gonna do a unitary transformation that basically brings this Hamiltonian in diagonal form, okay? The Hamiltonian of the leads. I don't know what that transformation is, but what I'll know is that if I bring this to diagonal form, I'll also have to do the same to the interaction Hamiltonian. And what you'll find is that something that acts locally in configuration space is completely delocalized in energy space. Let's do the diagram. This representation here and this representation is exactly the same. All I've done is a energy transformation on the Hamiltonian of the leads, okay? That's what I was mentioning before, Paul. These are both equivalent representations. One of them acts locally in configuration space, and the other one is completely delocalized in energy space.
It's like taking the norm. It's like taking the normal modes of the chain.
Exactly. Exactly that. Okay. I want to be clear on that because the next step is going to be very important for me to use that basis. Okay. What have I done? I've done nothing. Okay. I've moved from a chain to something that looks like a star via a unitary transformation. That's all I've done. You still require an infinite amount of degrees of freedom for you to properly describe an appropriate bath. Yeah. Landauer theory still holds, and I still need an infinite amount of degrees of freedom. Okay. But here's the kicker. What if you put a Markovian embedding on each one of these modes separately in such a way that you can keep each one of these modes finite? Okay. This is our Markovian embedding right here. Now, what I've done is very phenomenologically shown you how you can do a Markovian embedding on multiple modes in such a way that you recover Landauer's theory. In this case, you're going to get a master equation, because of the fact that the embedding is Markovian, so you can justify all the approximations that lead you to a Markov equation, okay? To Lindblad.
This part exactly. You said to each mode. What
Yeah. So unfortunately, this is not the best picture because I have the single bath. But the main idea is that each one of these modes couples to a Lindblad bath, each one of them with a different gamma, and each one of these modes has different energy. And the effect of the residual bath that I have next to each of the modes is to bring it to thermal equilibrium at the energy of each of the mode.
But then that's in addition to the original Hamiltonian or a transformation of the original?
The original Hamiltonian is just the central system. I'm just trying to find a way to make this guy think that it's connected to an infinite reservoir.
Okay, so I thought that the original, the impurity is connected, whatever it is connected to those two chains, left and right.
Yeah, that's the reservoir. That's the
Yeah,
reservoir.
Right,
Yeah.
Exactly. Are you just doing a transformation of this, or are you adding the secondary baths?
again, that's the reason I said I'm doing this phenomenologically, because I thought that was easier for people to understand than going back through all the derivations. But we agree up until this point. Do we agree? Then why not just phenomenologically add an infinite reservoir here that you can describe via Lindblad description? Why not? What's wrong with that?
You're changing the Hamiltonian. The system, the whole thing is not the same as you started with, if I understand correctly.
Well, the Hamiltonian that I care about is the Hamiltonian of the system.
No,
The rest is a the rest is a construction that I built in such a way that I can make the system think that it's coupled to an infinite reservoir.
Right, but I can study electron transfer in a spin bottle model, can study electron transfer in a liquid or in another liquid, right? And the environments are, if they're different, the process I'm observing is very different.
I would disagree.
Here we sort of talk about environments of environments, right? So when if you add these, so this is, I think maybe we can translate it, right? Because here you just add these environments for your environment to be in a thermal state. Do I understand that correctly?
That's exactly it. That's exactly it.
So
Yeah.
the way he's changing, he's adding an environment to the environment.
Yeah.
Sets the environment, the first
Yeah.
environment to the thermal.
And the key aspect,
And
and the key
you
aspect
can
is
justify this maybe something when I
That's
look
exact-
out into the math.
that's exactly it. Yeah, yeah, yeah. If you want to be formal about it, we have to go through the derivation. This is just a way for me to make clear to other people, okay?
But it doesn't necessarily mean that the dynamics you're going to observe with this is going to be the same as the dynamics we would have observed without.
What makes you say that?
I mean, technically, she's right? It's a different system. I mean, but you
Different
must
photons.
be approximating.
Well, it's strange that you say that to me, because you believed me when I did the Markovian embedding via reaction coordinate mapping.
I didn't quite understand what you said.
Well, the dynamics of this problem are also well captured with this Markovian embedding for that spectral function.
So
That's been shown, yeah? That's been shown.
What I thought you were doing is that you are you are taking, say, one mode out of the bath and putting it as a system.
Yeah.
It's an exact transformation.
Yes.
Says how to do this with
Yes.
exchange of spectral density. That's an exact. I'm aware of
Yes,
that.
I'm doing exactly the same, but I'm doing it multiple times.
Calvin had a question.
Yeah.
I mean, I think it's the same comment, but in general, if you just added these red and blue things, it will be different. But it seems to me that you're doing it in a very special way. Preserve something about the dynamics you care about. Is that right?
Yeah, well, yeah.
So I don't think you can just.
So the thing is that the idea,
You do it in a very special way.
But
this phenomenological derivation, it was just intended as an idea for me to explain what I'm doing, not that it's derived in such a way. If you want to be formal about it, I mean, I'm not going to come here with a bunch of equations. Yeah.
is it a transformation of the bath Hamiltonians, or is it an addition of additional baths?
I'm telling you that this description, where I have an infinite amount of degrees of freedom in the bath, and this description, where I add some auxiliary reservoirs to thermalize each of these modes, is equivalent.
So you can show that. All right. But
So I think for time, we should let him kind of continue with.
Yeah.
But we can come back to this.
Okay, then you get your master equation that describes the entire dynamics. What's the cost? The cost is that now you have to keep track of not only the degrees of freedom of your system, but also the degrees of freedom of the modes that you employ here to model your reservoir. Okay? This is an old idea, by the way. This is not my idea. This came back from the 90s. The only difference is that we put it in a formal setting, in a mathematical way. Back then, it was just phenomenological. Let's put reservoirs on top of each of these modes and see what happens.
is that the pseudo mode? Or
It has so many names: pseudo mode, thermofield. Yeah, it's an idea that comes back from the 90s. Yeah. All right, and now the key point is that we can keep n finite. And why is it that I'm trying too hard and so hard to keep n finite? And that's because at some point I'll want to model this system along with the degrees of freedom of my enlarged system. And if this is infinite, there's no way for me to keep track of all those degrees of freedom. Okay? Look at what I'm doing at the level of the spectral functions. I hope you understand my handwriting is not the best. If I have a system coupled to a single fermionic mode, and that fermionic mode is coupled to a residual reservoir, for which by construction I impose that this residual bath couples to this mode with a flat spectral function, the effective spectral function that the system will see is a Lorentzian. Okay? You can show this analytically. What I'm doing by this mode construction is that I'm basically approximating the spectral function, the original spectral function of the original problem by a sum of Lorentzians. And in such a way, you can approximate any spectral function you want. Of course, it probably has to satisfy certain mathematical conditions like not being discontinuous or very peaky or stuff like that. Okay? So that's what I'm doing. Any questions? All right, let's carry on. Let's look at some results. If I have the resonant level model, okay, as your central system, it's a very simple model that you can solve with Landauer, but we wanted to use it as a benchmark. You can look at the power and the efficiency. What I'm showing you here is the power, these two butterflies here. This is the power computed with Landauer, and this is the power computed with our approach, okay? And you'll see that there's some wiggly parts here that are not well captured. That's because we selected a finite bandwidth on the problem, just so that we can showcase what happens if you have a finite bandwidth. But this can be taken further away very, very easily for quadratic models, okay? And this is what happens as a function of the system lead coupling. This is actually been observed in many different models with many different techniques, is that the maximum power starts to increase as you increase the coupling to your bath, but then at some point it starts to go back down, okay? And
quick question.
yeah.
By doing this, are you ending up with a larger system?
Yeah, it's a larger system.
So yeah, don't you have then exponential scaling with the number of those of the modes that you include in the system?
Not an exponential number. You basically have to select enough.
Not an exponential number, but the Hilbert space grows exponentially with the number of modes.
Not in this quadratic model. We're going to talk about non-quadratic models in just a second. Yeah. This quadratic model, everything's Wick's theorem, so you can just factorize everything into 2-point correlations.
So you're saying it does grow exponentially, but it doesn't matter because you can do things analytically.
This is a fermionic quadratic problem, so everything is Gaussian, and all the dynamics.
States. It's just that you can deal with them analytically.
Yeah, same as.
Q to the n is exponential.
Yeah. But for fermionic systems, when you have non-quadratic interactions, everything is single particle physics. Okay. Yeah.
But if you're going to write a path integral, you're going to need to.
I'm not writing a path.
You're not.
Yeah. No. Whenever I get like something like non-quadratic interactions, then particles start talking to each other, and then things scale like 2 to the n. That problem will be tackled in just a second. Okay. Right. So something that happens with the effect of strong coupling is that the efficiency is always decreasing, which is bad. Yeah. At least for strong coupling thermodynamics. Okay, that's just one example. Another important thing. How much time do I have? Okay. I'll be careful with the questions I'll answer right now, otherwise I won't have time to finish. Okay. Is that okay with you? Yeah. Yeah, Gerald, this is the paper in which we show that the 2-point correlation functions are also well captured. Basically, what we do is some full counting statistics. I don't know if you're familiar with that.
Yeah.
And that gives you basically all the moments of the particle current distributions and all the heat distributions, and everything is thermodynamically consistent, which is something that we really care about because we do thermodynamics. Yeah, yeah. And we also look at this entropy production to make sure that everything at the level of really the appropriate thermodynamics is consistent with this framework. This is unpublished, but it'll come soon. All right, we have our bath description after a long fight. What do? We basically discretize the reservoir into a collection of modes, each of which is subject to thermal dissipation via Lindblad operators. Okay? We've got our bath description. But what we really want to solve is something that's very complicated as a central system, something like an interacting many-body system in the middle, okay? And this is where our favorite ansatz come into place, okay? And now that I have a bath description with a finite number of degrees of freedom, I can employ an MPS and see how things will look like, okay? All right, there's gonna be two complications. The first one is that the star configuration that I described before leads to known local interactions between your system and your bath, okay? To those of you initiated in the subtle art and the kung fu of MPS, know that long-range interactions are usually a problem, okay? What is it that people usually do? TDVP, yeah? Although this is a fermionic problem, and the problem is that these known local interactions would lead to known local Jordan-Wigner strings, okay? And that makes TDVP a bit problematic, okay? So we're gonna have to solve this using swap gates. I know what you're thinking. The employment of swap gates to deal with known local interactions is usually considered to be bad. The main idea, to those of you that don't know, is that when you do these swap gates, the correlations will be spread across your system very rapidly, and you won't be able to get very far in time before your bond dimension explodes, okay?
Sorry, non-local in what again?
The interactions are non-local because this side of your system couples to all the modes in your reservoir.
But so does the system mode couple? The system comes from the modes. What do you mean by non-local?
Again,
They go
The
from
one
arbitrary
EGO.
distance.
yeah, we're talking about two.
They're kind of large over an arbitrary distance.
Yeah. There's two spaces here, configurational and energy. If I take this to configuration space, the interaction is non-local because in energy, we talked about this, yeah?
I guess the setting here is that you've ordered them in a 1D way.
Exactly.
That gives a sense of distance, sort of artificially, but
Exactly.
in that embedding.
Well, they have to do it, right? If I want to put it in an MPS, an MPO.
Right.
Yeah.
Maybe that context helps.
Okay,
But
yeah.
transform to the normal modes or something like this, or the change.
Yeah. So the thing is that
We use a 1D method.
I have to use a 1D approach, a tensor network. And if I do that, I'm going to have objects constructed in a 1D array, and there's going to be objects on the right side that interact with all of the guys on the left. Okay?
Sorry, I think you wanted to kind of get through. Maybe
Let's do it.
I'd like to get to the end so I can see a kind of overview. I don't know about anybody else, but I'm
Brilliant. Thank you very much, Paul.
bogged down a bit in details here.
Brilliant. All right. So this is the direction we went with, swap gates, which is typically not good in the community. Yeah, people don't really use them because of this reason. They believe the correlations will be spread all over the place very fast, and then your bond dimension will basically explode. However, we have another thing. We have dissipation on these modes. And the dissipation that's bringing each of these modes to its own thermal equilibrium, it's killing those correlations that will be spread by the system. And that's the reason this method works, okay? So the entire method is based on a Trotter decomposition of the Liouville propagator, combined with some swap gates and some extension on the, because now we have an open system, so we have to extend your Hilbert space in a certain way. And then by this circuit right here, if you go back and forth through your circuit, then you get an evolution of, or an initial state one point in time. You do this multiple times to reach the steady state. All right? Some results. This is one of my favorite ones. To those of you who are familiar with this Carter-Parisi song exponent in transport, this is something that can be observed from the anisotropic Heisenberg model. Okay? And that's something that we wanted to observe. This is an effect that occurs at infinite temperature. So infinite temperature physics is not trivial when you talk about many body systems, okay? If you talk about simple models like spin boson model, like infinite temperature physics is completely trivial, but for many body systems it's not, yeah? And this decay, so what I'm showing you here is the value of the currents, both energy and particle currents, as a function of the system size in a log-log scale. And this exponent here, this 0.5, is the super diffuse exponent that falls into the universality class of the KP set, and decay of correlations. This is something we managed to observe with this method, and we're very, very happy about it. Not a new result, just corroborating something that we already knew that we can capture with this method. Now that we have something new, something we can look at is thermal machines when you have like non-quadratic interactions, something that hasn't been explored in the past appropriately. We basically have some model with interacting fermions, the fermions interacting with each other with a certain parameter u. And then what we can do is, sorry, we can consider what happens when you look at a thermal machine at the power, efficiency, and the energy currents when you have no interactions and when you add some interactions. And the idea here is that repulsive interactions should lead to some detrimental effect. Yeah, there are some inelastic scattering effects happening, going around, that we expect will be detrimental to efficiency. But that's not the case. If you look at the black lines here, this is the non-interacting problem. And the red lines, this is the problem with some amount of interactions that is non-perturbative. The interesting aspect here is that you can get higher energy currents, higher power. That's not surprising. The surprising bit is that you get it at higher efficiency. So non-quadratic interactions may not be a detrimental effect. Okay, there might be a resource. And that's the point I wanted to make with this talk. My take is that nothing comes for free. My take is that probably the fluctuations here are the fluctuations as soon as you add the interactions are larger. That's at least what I think. But I haven't shown it, okay? Just to summarize this three-body problem that I showed you, this is just with three interacting fermions in the middle. And it shows very interesting behavior. It shows us that non-quadratic interactions may be a resource, okay? And finally, and most importantly, I think this method is primed to do many sorts of different things. When you have like very complicated central systems, I think this is the way to go. And I think this is something that hasn't been explored in the methods that we've seen up until now, which are mostly primed for small systems, whereas this, you can do hundreds of spins and stuff like that, okay? If someone tells you about a new method and doesn't tell you about the limitations, they're either lying to you or lying to themselves. This is something that always worried me, low temperature physics, okay? The low temperature regime is the regime in which this method struggles. The reason being that at low temperature, the Fermi-Dirac distribution becomes sort of discontinuous. And you need to pack a lot of modes around the Fermi level such that you can capture the correct physics. That could make the problem intractable. However, there's the beautiful work by Swalak, von Delft, and Neil Lambert that showed that using this method, they managed to get all the nice Kondo phenomena like the Kondo conductance peaks and so on and so forth. Okay? Something that I'm very interested in, not other people are not really that interested in that, but I'm very interested in fluctuations, yeah, like not just looking at energy currents or looking at particle currents, but look at how they fluctuate. That's very important in my opinion, because the fluctuations is really what tells you everything about the thermodynamics. Whenever I have quadratic systems, I know how to compute effectively and accurately those fluctuations. But as soon as I add the non-quadratic interactions, I face several limitations. To those of you who are familiar with tensor networks, I'll tell you what the problem is. At some point, computing the statistics of work and particle currents amounts to taking the trace of your density matrix as a function of a parameter. And the idea is that the trace will be not normalized because of this parameter. And you want to see how far away you are from normalization because of this parameter. This is something called full counting statistics. But whenever you do any tensor network, you have to renormalize the state if you do TBD or time DMRG or anything like that. So you have to normalize it.
But you can always keep track of the norm.
You can keep track of the norm you're losing, even though you're truncating the bond dimension? I don't think so.
Well, if you truncate, no. But
Well, you have to truncate at some point, yeah?
You can in that case, actually.
We'll talk about it because this is, there's something to be exploited here. If we manage to solve that problem, we can capitalize. Okay. Bosonic systems, I haven't really thought about it. My take is that probably it's more complicated because now you have, as opposed to having single modes, which is just fermionic, now you have many levels on your bosonic mode. Although at the technical level, it's a bit easier because we don't have to account for Fermi statistics, so on and so forth. So this might be a nice extension, or maybe other Markovian embeddings. That's it for my talk. Thank you very much.
5 minutes for questions. So, Steve and Joe.
If you has a question, or I would have an uncontroversial comment.
Okay, yeah, let's start with the question first. Yes.
So boring. Don't ask it then. Yeah.
Did you have a question? Yeah. Okay, great. Yeah.
So you compared with Landauer theory, but even though Landauer theory is actually it's an approximation that works in the weak coupling limit.
No, it's not.
What do you mean? You have to actually use the non-equilibrium function approach.
No. That's only if you look at interacting systems. For quadratic systems, it's perfectly exact. You can compute the transmission functions and the lead the lead system coupling can be made to anything you want. You're thinking about using these Green's functions when you have interacting problems. There, it's an approximate method.
Yes.
That probably usually you do it only a weak coupling. But yeah, but if everything's quadratic in fermion language, everything is completely exact. Yeah.
Did you have one, Benedict, first?
Yeah.
or also a comment.
Yeah, go for it.
Sorry. It shouldn't matter whether you do swap gates or TDBP or whatever.
Yeah.
In a sense, because you're just approximating the propagation.
And the correlation, yeah.
It's a technical detail, but the entanglement in the state, it's close to exact, should be the same.
Yeah. It's just that when I was talking about this method to some of the people in the tensor network community, they were always jumping at the fact that don't do swap gates. And then that was basically part of my argument along those lines. Yeah. Thank you very much. Yeah, Nancy, maybe. Yeah.
So I'm confused. I didn't understand what you're doing because at the beginning I thought you're taking a train which has coupled degrees of freedom and you're transforming to normal modes or something like that to get back modes that don't couple to each other. But then later, I think you said that you go back.
Of course, they'll couple to each other afterwards. Of course, if you have non-quadratic interactions. You see the Siebernet Kondo physics, right? You have
quadratic in what? In what?
Quadratic in fermions, in fermion fields.
I thought that the atoms or whatever the particles showed on the train. I thought these are
Non-interacting.
lattice monomodes.
No, they're
Okay, but
fermionic
nothing
modes.
is
It's fermionic modes.
everything.
Everything's fermionic. Everything's
What
fermionic.
if it were to be bosonic? Then
Well, maybe you can help me with that.
so you're saying it's specific to.
Yes,
Okay, I didn't understand that.
yes.
But still, all right, so still, when you do a transformation, so you're going back to the original representation where each fermionic equilibrium is coupled with nearest neighbors, is that what you're doing? Which representation do you work with in the end?
The one in which each of the modes is described by an energy level like this, where this Hamiltonian is diagonal, but the interaction Hamiltonian is not, it's completely delocalized. Yeah. Kevin, yeah.
So when you do this mapping where you do this Markovian embedding,
Yeah.
you need to know the specifics of the Hamiltonian and so on. In other words, they give you a different system, you'll have to cook up a new recipe to do it. Is that correct? Or?
Well, all you need to know is that all you need to know is that the Hamiltonian of the elites is quadratic in fermion language. That's a requirement.
Well, I mean, I can move to a completely different type of system. The reason I ask is that if you think about what the process tensor does, it does something similar because you just look at the system mapping.
Mm-hmm.
So if you look at the process tensor as a function of number of time steps.
I'll be completely honest with you, Kevin. I don't immediately see a trivial way for which you can compare this to a process tensor, because a process tensor keeps track of all the memory.
Well, I mean, yes, like so do you. And you
I do it by keeping track of the modes, of the dynamics of the modes, right, which is different, yeah?
I don't think so.
You don't? Yeah.
No. It's effectively you're keeping track of anything that will impact your dynamics later. And you can do that in a system agnostic way. Yeah.
We can do that in a. How you can do it in a system agnostic way if it's non-Markovian? That's the whole point of being non-Markovian, that the system affects your reservoir.
No, I mean you can do it without knowing any of the details of the Hamiltonian.
I think it's just agnostic mathematical formulas.
I see. I see.
Not that the numbers would be the same.
I see.